Okay, so in today's quiz, we're dealing with mass mole conversions and an empirical and molecular formula problem. So first and foremost, we're asked to calculate the moles of ethanol in 10 milliliters of ethanol. Thankfully, ethanol is the alcohol we can drink. Methanol you can't drink or you'll go blind. So we're starting from the volume, which is milliliters, and in the end, we want to report the moles of ethanol, which is CH3CH2OH. It's a typical organic compound. The exact identity of this compound is not important, but we do know its formula, so we can calculate some useful things. So first, if we want to calculate moles, where do we typically calculate moles from? Molar mass and what initial quantity? Grams, exactly. So we're going to go to grams of ethanol. And as our classmates astutely pointed out, we will use our molar mass as a conversion factor to go from grams to moles. Perfect. How do we get from milliliters to grams? How do we get from volume to mass? What conversion factor do we use? What conversion factor do we have that relates grams, mass, and milliliters, volume? Density, exactly. So we're going to use the density as our conversion factor. Have we done volume to mass conversions before in chapter 1? Yep. This time we're applying it to a compound as part of a mass mole conversion. So now that we have our scheme in place, let's now execute on that scheme. We have 10 milliliters of ethanol. If we're going from milliliters to grams, what units need to be on top? What units need to be on top? Grams, exactly. So we're going to multiply by our conversion factor of density. So we have 0.8 grams for every 1 milliliter. And this is grams of what? Grams of ethanol. Okay, for our next step, if we're going from grams to moles, what units need to be on top? Moles. So then, in 1 mole of ethanol, we have how many grams? Let's do this sidebar calculation. Let's take care of this sidebar calculation. So for our molar mass, let's break down the formula and let's calculate it. So the molar mass, we have to add the mass of every single atom of every single element. So carbon has a mass of about 12 grams per mole. And how many carbon atoms do we have in ethanol? 2. Okay, hydrogen has a mass of 1 gram per mole. And we have how many hydrogens? 6, exactly. Finally, what is the mass of oxygen? 16, so we have 16 gram per mole, and we have how many oxygen atoms? 1, exactly right. So if we punch that into our calculator, 12 times 2 plus 6 plus 16 gives us a molar mass of 46. Okay, is everyone following so far? Now all we have to do is punch this into our calculator. So let's go to the calculator interface. So we have 10 times 0.8 divided by 46. And that gives us 0.17 moles that we round to how many sig figs? How many sig figs do we round it to? How many sig figs does 10 have? 1. So then we'd report our answer as just 0.2. Oops, let me just fix that really quickly. So we have 0.2 moles of ethanol. And I always like to specify moles of what? I prefer to specify my compound identity, so that way I always keep my number in order and I make sure my order of magnitude is reasonable. Does that make sense? Okay. So let's now look at an empirical formula problem. So let's say what we know. So we know in this compound we have 1.5 moles of sulfur and we have 2.25 moles of oxygen. Okay, So we're given the moles of each element. We are also given the molar mass. Okay, we have a lot of information to work with in this problem, and we have enough information present here to calculate the empirical and the molecular formula. So recalling from last time, if we're starting from moles, where do we go from moles? What's the first step if we're calculating the empirical formula, which fundamentally is a ratio of what? The empirical formula, as we talked about last time again and again, what is it a ratio of? Moles. It's a mole ratio. So then we have both of our mole quantities. So what are we going to do? Divide, yes. We're going to take the ratio. And ideally, we want to divide by the smallest quantity of moles. You do not have to, but it's by far easier than dividing by the largest quantity. So we're going to divide both of these quantities by 1.5 moles of sulfur. So in the end, after we divide both quantities by 1.5, we end up for our sulfur coefficient, we have 1. And then for our mole of oxygen per mole of sulfur, 2.25 divided by 1.5. Oops, 2.25 divided by 1.5. That in turn, we get, after punching this into our calculator, we have 1.5 moles of oxygen per every 1 mole of sulfur. Okay, we have a mole-to-mole ratio. Wonderful. Now my question to all of you is this a valid formula ratio? No. So then we need to convert this fraction into what? Whole numbers, exactly. So what are we going to multiply by? 1.5. So when we think 0.5, that corresponds to a fraction of 1/2. So what do we need to multiply our fraction by? How do you get a whole number from 1/2? How do you get rid of this 2 on the bottom? You multiply by 2, exactly. Okay, so we're going to multiply, and I always like to put my labels. So I'm going to choose 2 moles of sulfur, so my units cancel. I know it may seem weird to have a label, like why am I saying 2 moles of sulfur? Well, the goal of choosing this number and putting this label is so that way we know the subscript for sulfur. It makes it very clear. How many sulfur atoms do we have? How many sulfur atoms did we choose to have in this molecule? What did we pick? What number? 2, exactly. So it makes it very explicit. Okay, so in the end, after taking 1.5 times 2, we end up with 3 moles of oxygen. So our ending formula at the end of all of this, let's now write it down. So how many sulfur atoms do we have? How many did we calculate? What did we choose for our moles of sulfur? 2. So this is S2. And then how many moles of oxygen did we calculate in our mole ratio? 3. So it's S2O3. Now, we aren't done. This right here is our empirical formula. But we need to convert our empirical to the molecular formula. And to do that, we're going to need to calculate N, where N is equal to our molar mass of our molecule divided by the molar mass of our empirical subunit. So let's really quickly calculate the molar mass of this empirical subunit. Just like any other normal molar mass. Do we know the number of atoms and do we know their atomic masses? Yes. So sulfur is 32. We know we have 2 sulfur atoms. Oxygen is 16. And we have how many oxygens? How many oxygens do we have? 3. Okay. And in turn, if we punch that into our calculator, 32 times 2 plus 16 times 3, we end up with an empirical molar mass of 112 gram per mole. Now, where do we get our molar mass, our molecular molar mass? Are we given in the problem, are we given the molecular molar mass? Yes. So we know it's 224. So then that gives us a calculated N value of 2. So what do we do with this N value? How many of these S2O3 units am I going to write? So I have 1 written. If N is 2, how many of these S2O3 units am I going to write? Oh, wow, you guys are doing the multiplication step already. So in the end, we'll get S406. The way I like to think of it, you can either multiply all of your subscripts by 2, or you can draw out 2 S2O3 subunits and add your atoms together. Exactly right. So the formula of this compound is S406, which is a compound you'll actually be dealing with in the redox titration lab towards the end of the semester. Any questions on calculating the empirical and molecular formula from the moles? So just to recap once again, you write out the moles of each of your element, you take the mole to mole ratio. Then you convert all of your decimals into whole numbers by multiplying by a common whole number quantity, in this case 2. This 2, since our mole ratio is moles of oxygen to moles of sulfur, this 2 is signifying the moles of sulfur in our empirical formula. After multiplying, we see we have 3 moles of oxygen and 2 moles of sulfur. Then from there, we calculate the molar mass of this S2O3 empirical formula unit, and we calculate N by dividing our molar mass by the empirical subunit mass. We then get N equals 2, and we multiply all of our subscripts by N, which is 2. Does that make sense? Okay. So if we don't have, does anyone have any other questions on this example? If we're good on this example, we'll now move on and talk next about the remainder of chapter 4 and move on to chapter 5 today. So what we're going to do is we're going to really break down, and we're going to do an empirical and molecular formula calculation from scratch. So in order to lead us into this idea, let's look at an example we solved last class session to understand how to approach determining the molecular formula given the mass percent. So I'm going to showcase and I'm going to walk us through an example that we tackled last class session. So this is on page 40 of the notes. We're going to walk through this. We're going to talk through this example, and then I'm going to have you attempt an example on your own, okay? We've already done this problem together, but I want to make sure we remember how to approach these problems. So we are given the mass percent of each of our elements, and we are given the molar mass. Okay, wonderful. Now, we discussed and we derived an equation last session that relates our empirical formula, which is a mole to mole ratio, to the mass percentage of each element, right? So the mole to mole ratio is equal to the mass percentage of one element over its molar mass times the molar mass of the second element divided by the mass percent. This formula is in your notes, and you should either understand how to derive it, you should understand or memorize this formula, or you should understand how to, and most importantly, you need to understand how to use this formula. Okay, so we designated, and I always like to put labels. So I labeled N2, which is our moles of element 2, to be oxygen, and I labeled N1 to be phosphorus. I wrote down my mass percentage and molar mass. Where did I get my molar mass from? Where do I get my molar masses for each element from? Periodic table. You're just reading off from the periodic table the atomic mass. We then determined the mole to mole ratio by plugging in the mass percentage of oxygen over the molar mass of oxygen. So we have our moles of oxygen on top times the molar mass of phosphorus over the mass percentage of phosphorus. That in turn gave us our mole to mole ratio, which in the end we get a nice clean decimal. If your decimal is really weird, it does not look like any of the ones in the table, try a range of whole number multiples, but if it's not resolving at all, you may want to go back and double check this initial calculation, okay? So we get a fraction of 1.5 moles of oxygen per 1 mole of phosphorus. How do we convert this 1.5 into a whole number? Does that look familiar from the quiz? Yeah, we multiply it by 2. That was intentional, by the way. So we end up with an empirical formula of P2O3. Does that also look familiar from the quiz? And the reason why I'm bringing this up is that to study for the quiz, it's always best to look at the prior notes and any homework assignments I provide. I'm not making you go too far off the beaten path for preparation. Okay, so now that we have our empirical formula, we calculate our molar mass of this empirical subunit, and we compare it to our molecular weight. We then calculate N by taking our molecular weight over our empirical subunit mass. That gives us an N of 2. So what do we multiply all of our subscripts by? 2. Okay. Now, what we're going to do is I'm going to give you the mass percentage of each element in a compound, and you're going to calculate the molecular formula of the compound. And the only thing that you do differently for a 3-component system is when you write N2 over N1, you're going to use your equation as normal. So it's the mass percentage of 2 over the mass percentage of 1. Oh, mass percentage of 2 over the molar mass of 1. Oh, sorry, mass percentage of 2 over the molar mass of 2 times the molar mass of 1 over the mass percentage of 1. I started writing the other form of this equation on accident. Okay, the only thing that changes when you have a 2-component system, you're going to want to make sure you're dividing by the same mole quantity in each case. So we'd have another equation to describe N3 over N1, which is the mass percentage of 3 over the molar mass of 3 times the molar mass of 1 over the mass percentage of 1. So the key feature of a 3-component system is you want to make sure that you divide by the same moles of a given element. So do you notice how N1 is on the bottom in both of these? And it's so that way you can actually use this mole-to-mole ratio to derive an empirical formula. Just like how we divided the moles by the smallest quantity of moles, we want to make sure we're dividing each of our moles by the same number. So I'll let you loose on this problem, take a few moments to compute out the mole-to-mole ratios, and then try to convert this mole-to-mole ratio into a whole number empirical formula, and then take that empirical formula and use the molar mass ratio to convert it to a molecular formula. So this is a type of problem that you may see on an exam. So I want you to take some time. Don't be shy to talk with your partners, and I'll be walking around to check to see how it goes. Yes? Mm-hmm. Yes. No, you keep them separate, since this is the moles of hydrogen per mole of carbon. So let's put this label next to this. So now you already have your mole-to-mole ratio. And what you're going to try to do is you have decimals. You're going to pick a whole number that allows you to multiply both of these numbers by, that would give you that would get rid of your fraction. Yes, yes. And you have to remember, when you have your mole-to-mole ratio, you multiply everything by this. So you're going to multiply everything. So you multiply this number by 3 and this. Yes, and then you do the same process to convert the decimal. We keep thinking about the mole-to-mole ratio must be fixed. So you need to multiply the hydrogen. Yes, yes. Everything going okay?
Oh, I was just asking like if the matter was taking.
You'll need both. Because the first one is for the ratio, for example, carbon to hydrogen.
Okay.
The second one is the ratio of oxygen to hydrogen.
Okay.
And the key thing is you divide by the formulas of the same element. avoid the equation.
So technically using both there's 3 elements.
Yes, exactly. Oh, did you round? Well, oh no, this one did come off as like a super clean number. Yeah, that means it's also good. Yep. 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 More than okay. Go on. Any questions? Any questions? Any questions? Yes. Let's see. Or just double check your calculations in your calculator. The setup looks good. Everything going okay? No, that's fine. That's fine. That'll work. That'll work. Everything going okay? Let's see. Yep. Yep. Looks good. Yep. Looks fine. Yep. Looks fine. Oh yeah, that's more than okay. That's more than okay. Looks good. Looks good. Everything going okay? Okay. Yep. And you're getting nice clean numbers for your ratio.
Yeah.
Yep. Okay, I see actually a lot of reasonable solutions for this problem. So what we're going to do now is we're going to plug in, and we're going to first label each of our quantities, and then we're going to plug in some numbers. So we have our equations all conveniently set up and ready to go. So let's put some labels now. So I'm going to label carbon. So I'm going to label carbon as N1. It's perfectly arbitrary, but and it doesn't matter what you label as N1, but I'm just going to pick carbon since it's the first one. Makes my life easier. Next, I'm going to label hydrogen as N2, and let me use a different color pen for that. Okay, and then finally, I'm going to label oxygen as N3. Okay, perfect. So I have all of my labels established. One moment. So now that I have all my labels established, what we're going to do is we're going to plug in the mass percentages and the molar masses. Okay, so N2, which is hydrogen, let's now plug in the mass percentage of hydrogen, which is 9.7%. We're then going to divide by the molar mass. And what is the molar mass of hydrogen about? Yep, 1.008. Okay, perfect. We're then going to multiply. We're then going to multiply by the molar mass of element 1. What is element 1 and what is its molar mass? Carbon, and what's its molar mass? 12. Okay. And then we're going to divide by the mass percentage of carbon. Okay? We're just going to plug in the numbers for now. We're next going to look at the ratio of N3 to N1. What is the mass percentage of N3? What is N3? What did we label as N3? Yep, 51.6, which is the mass percentage of oxygen. What is the molar mass of oxygen? 16. Okay, and then we're dividing by the moles of carbon, and we already know our expression for the moles of carbon, which is the molar mass over the mass percentage. Wonderful. Okay, so we have the schematic prepared. Let's now punch these numbers into our calculator, and let's write a ratio of N2 over N1. So if we punch N2 over N1 into our calculator, we have 9.7 over 1.008 times 12 divided by 38.7. And a sign that you've done something right is your number should almost perfectly match. It should be within 0.02 at most. So this is one case where you can round. You're never supposed to round unless your number is within about 0.02. So this is very, very close to what number? 2.98 is almost infinitely close to 3. So this is one case where we can round it to 3. And so if we're taking N2 over N1, we have 3 moles of hydrogen per 1 mole of what? What are we dividing by? What moles are we dividing by? What did we label as, whoops, what did we label as N1? What did we label as N1? Carbon. So this is the moles of hydrogen per every 1 mole of carbon. Perfect. Does that make sense so far? Okay. Now we're going to look at N3 over N1. And if we punch that into our calculator, let's punch that into our calculator right now. 51.6 divided by 16 times 12 divided by 38.7. And that in turn gives us, and this is a sign you're doing something right, 1. There we go. So this tells us we have 1 mole of oxygen per every 1 mole of what? 1 mole of what? What is our mole ratio with respect to? 1 mole of carbon. Okay. Don't forget these labels. These labels will save you if you're ever stuck. Okay, so now we have our mole to mole ratio. Do we have clean whole numbers? Yes. So then let's write, so how many carbons do we have? How many carbons do we have? 1. We see 1 mole of carbon in all of our ratios. How many hydrogens do we have? 3. Exactly. And how many oxygens do we have? 1. Yep. You're also welcome to do this process, the longhand method. You will get the same answer. So whatever works. I just like efficient methods, and it's just my personal preference. Okay. Now we are ready to begin the next phase of this problem. Now we're ready to begin the next phase of this problem. What is the molecular mass? What is the mass of our molecule? What mass are we given for our molecule? 67. Okay. 62. 62. Okay. 62.07 gram per mole. Okay, perfect. So we know our molecular mass. Let's now calculate our empirical subunit mass. Let's calculate the molar mass of our empirical subunit. Okay, can we do that? Can we calculate molar masses? Are we good at that? Yeah, we're pretty good at that. So we're going to take the mass of carbon plus 3 hydrogens times the mass of hydrogen plus the mass of oxygen. So if we add that together, we get 12 plus 3 plus 16. That gives us 31 gram per mole. Do we have enough information now to calculate N? Do we have enough information to calculate N? Yes. So we're going to take our 62.07 gram per mole, which is our molecular mass, and divide it by 31 gram per mole, which is our empirical subunit mass. That gives us an N value of 2. So then, what do we do to all of our subscripts? So we have CH3O or C1H3O1. What do we multiply all of our subscripts by? Yep, exactly right. And that in turn gives us C2H6O2. Does that make sense? Okay. So let's now apply this idea of empirical and molecular formula to a very interesting case. Who here is interested in material science? Polymer chemistry, maybe? Plastics. Okay. Let's talk about the building blocks of modern society, I suppose. So polymers, we handle these on a day-to-day basis. These are highly conceptually related to this idea of empirical and molecular formula. Well, polymers are super large molecular weight compounds composed of a repeating monomer unit. Where does that phrase sound familiar? A repeating subunit. Does that remind us a lot of the empirical formula? A repeating molecular subunit? Yeah. So the monomer unit is the smallest repeating molecular formula in a polymer. Okay. So these polymers are everything from nylon to Kevlar to Teflon. We've styrofoam cups is polystyrene. So the degree of polymerization, I want you to think of the degree of polymerization as like the N of polymers. So this is like N for polymers. It is, quite simply, the number of monomer units in a polymer. So let me give you a classic example. So this wonderful molecule is known as styrene. It's of the formula C8H5678, C8H8. So this is known as styrene, the principal monomer unit of styrofoam cups. Now, if you start to chain styrene together, you can end up with a long repeating chain where if you zoom in on your repeating subunit, if you zoom in on your repeating subunit, we've essentially strung together this unit of C8H8 thousands of times. So to get a sense of the weight of all of these polymers, let's calculate the mass of a single styrene molecule, and let's calculate the mass of this bulky polystyrene polymer. So let's do this together. Can we calculate the molar mass? Can we calculate, for example, the empirical subunit mass if we know the formula? We can, right? So what's the mass of carbon? 12. So we have 12 grams. And how many carbon atoms do we have? 8. Okay, we're then going to add 8 times the mass of hydrogen, which is 1 gram. And if we add that together, 12 times 8 plus 8, we get a mass of 104 gram per mole. Now, if I said this polymer has 1,000 styrene units, what is our N in this case? What is our N? How many of these little styrene units do we have? 1,000. Exactly right. Polymers are massively heavy, so we know that our N is 1,000. So if we want to calculate our molecular weight, we take 104 gram per mole and we multiply by 1,000. And that in turn gives us 104,000 gram per mole. So it's probably larger than any other molecule and molar mass that you've seen to date. Another example of polymeric-like structures are polypeptide chains, such as in spider silk. Now, what I'm going to have you do is, so let's take a look at the polystyrene monomer. So the polystyrene monomer, again, is just styrene. And when we combine and we link together these styrene molecules via polymerization, we can generate large, higher order structures, such as your polystyrene cup or styrene packing foam. What I want you to do is to apply what we've learned for empirical formula, molecular formula, and N to a new case where we look at polyvinyl chloride, or PVC. So a sample was found to have these 3 mass percentages. So I want you to tell me the mole percentage of each element, the empirical formula, and then I want you to tell me the molecular formula. So try to think a little bit on how you can calculate the mole percentage, but if you're having trouble with question 1, try tackling questions 2 and 3 first. Just because I write questions in a certain order doesn't necessarily mean they need to be solved in a certain order. So I would suggest starting with 2 and 3 and then going back to number 1 with that information. And just stylistically, before I let you loose, why am I telling you to calculate the molecular formula before you calculate mole percent? Is it easy if we know the formula to calculate mole percent? Yeah, super easy, right? So let's get the formula out of the way first. Everything going okay? No problem. Everything going okay? Any questions so far? Okay. Any questions so far? Looks good. Yep, looks good. Everything going okay? Everything going okay? Looks good. Everything going okay? Yeah, looks good. Yeah, is that? Oh, 0.67 is 2/3. 2/3? Yep. Oh, yes. And the way you can tell that is if you go 0.67 times 3, you get up to. Everything going okay? That looks good so far. Everything going okay? Yep. Any questions so far? Any questions? Okay. Yes. Yep. Yep. And just write the mole labels. So this is the ratio of the moles of what to the moles of what?
Yeah.
Oh, what is this?
Oh, it's the hydrogen table.
Yes, exactly right. Everything going okay? You put down all of your data, and then go to the next slide. Going. Yep, yep.
Yeah.
With nice clean mole ratios. Everything looks good from there. Everything going okay? Yep, looks fine so far. Oh, and just remember, if you're using this method, make sure you label both moles in the mole ratio.
Yeah.
Yep, looks good so far. And just make sure when you write out these numbers, you write the moles, the numbers correspond to.
Okay.
Yep, exactly. Yep, looks good. The only thing is you're going to have to modify both of these ratios to get whole numbers. So this is still 1, but this is 1 and 1/2. So you're going to need to find a whole number to multiply both these ratios by to get out and remove that fraction. So in this case, to get rid of this 2 on the bottom, we multiply both of them by 2. Okay, I saw a lot of reasonable answers moving forward, and I really saw a lot of the fundamental capability to calculate the empirical formula, which is really what I'm looking for in this case. So I'm going to label carbon as N. Whoops, let me use a different pen color. So I'm going to label carbon as N1, hydrogen as N2, and chlorine as N3. It's perfectly arbitrary, but this is just what I'm going to choose for this example. I'm going to look at the ratios of moles of element 2 over moles of element 1. So then, what did I designate as element 2? Hydrogen. So I'm going to take the mass percentage of hydrogen, which is 4.8%, and divide by the molar mass of 1.008 gram per mole. Now, if I'm dividing by the moles of element 1, what did I designate as element 1? Carbon. Okay, so I'm going to multiply by the molar mass of carbon, which is 12.01 gram per mole, and I'm going to divide by the mass percentage, which is 38.7%. Okay, and this time we're just going to punch this into our calculator right away. So we have 4.8 divided by 1.008 times 12.01 divided by 38.7. And that gives us a number that is staggeringly close to 1.5. So then we know that we have 1.5 moles of what per 1 mole of what? What is on top? What is N2? Hydrogen. So this is moles of hydrogen per 1 mole of carbon. This is important. If you mess up your labels, you can end up with an answer that's substantially off, and you may end up assigning your subscripts incorrectly. Let's now look at N3 over N1. So what is element 3? Chlorine. So we're going to take our mass percentage of chlorine, which is 56.5%, divided by our molar mass, which is 35.45 gram per mole. We're then going to divide by the moles of carbon, and we're just writing the exact same expression, which is the molar mass of carbon over the mass percentage. And now we're ready to punch this into our calculator. So we're going to take 56.5 divided by 35.45 times 12.01 divided by 38.7. And that in turn gives us a number staggeringly close to 0.5. Exactly. So then we have 0.5 moles of what per 1 mole of carbon? What's N3 represent? Chlorine. Okay. Now we're ready. Now we're ready to do something interesting. Okay, so let's zoom out and refocus for a moment. So we know that N2 over N1 is equal to 1.5 moles of hydrogen per 1 mole of carbon. Now, we also know that N3 over N1 is equal to 0.5 moles of chlorine per 1 mole of carbon. And my question to all of you is, we have 2 decimals that have the same decimal. And my question to all of you is, how do we convert 0.5 into a whole number? What do we need to multiply that decimal by? 2. And since we have moles of carbon on the bottom, we're going to multiply by 2 moles of what? 2 moles of carbon, exactly. Okay, perfect. So in the end, after we punch this into our calculator, we end up with the following. We have 3 moles of hydrogen. We have how many moles of carbon again? 2, yeah. And then how many moles of chlorine? How many moles of chlorine do we have? 1. Okay, so then we have our preliminary empirical formula would be C2H3Cl. Okay, that's our preliminary empirical formula. Now we can calculate the molar mass of this empirical subunit. So let's do just that. So let's calculate the molar mass of this empirical subunit. by adding up the mass of each of our component elements. So we have 12 grams per mole for carbon, and we have how many carbon atoms? 2. Okay, we add up 1 gram per mole times 3 for hydrogen, and chlorine is about 35. And that in turn gives us the molar mass of our empirical unit to be 12 times 2 plus 3 plus 35. That gives us a molar mass of 62 gram per mole. We now are ready to calculate N. And in order to complete our calculation of N, we're going to need to use one more piece of information. So given N is our molar mass of our molecule over the molar mass of our empirical subunit, what were we given in the problem for our molar mass of this molecule? Let's go all the way up and check. What is the molecular weight of this molecule? 62,000. Polymers have large molecular weights, molar masses. So we have 62,000 gram per mole over 62 gram per mole. And that gives us an N value of 1,000. Okay, so what do we multiply all of these subscripts by? 1,000. This is why I prefer the multiplying method, because no, I'm not going to write out 1,000 of these subunits and then add my atoms together. That is a little bit silly. This is the reason why we invented multiplication, thankfully. Okay, so then that gives us a molecular formula of C instead of 2. What's 2 times 1,000? C2000. H instead of 3, it would be 3,000. And then Cl instead of 1, it would be 1,000. Exactly. So quite the interesting formula, right? So this is our molecular formula. From there, you can calculate the mole percentages quite easily. I'll leave that as an exercise for you to do at home, because this real focus, if you can get to the molecular formula, you'll be okay on the exam. But you want to be able to process these sorts of problems. Let's now handle some other analysis problems, some additional analysis problems that are inspired by your laboratories. So let's take a look. Just one moment, let me pull up the problem. Let's take a look at a pair of problems that are relevant to your exams and that are useful applications of the concepts learned in this chapter. So let me pull up the problem. Give me one moment to zoom in on it. So we're going to start the setup for this problem together, but I'm going to have you finish this problem on your own. So we took a sample of lithium metal. We took 2.00 grams of lithium metal and we burn it in the presence of oxygen. That in turn gives us 4.31 grams of a compound. So we have 4.31 grams of a compound containing lithium and oxygen. And what I want from you is to be able to determine the empirical formula of this lithium and oxygen containing compound. Now, there are many ways to go about this problem. If you are familiar with charge rules, you can even just predict the formula outright. However, you may not always be able to predict the formula just from the element identity. If this was a transition metal, you wouldn't be able to use that trick. So let's think through how we are able to go from the mass of reactant and the mass of product and determine the empirical formula. So what other information can we derive from these masses? If we know the mass of our reactant and we know the mass of our product, can we figure out how much oxygen ends up in our sample? What law can we invoke? What principle can we invoke? Conservation of mass, exactly right. So these 2 grams plus the mass of oxygen is going to be equal to the mass of our product, lithium oxide, right? So then the grams of oxygen are equal to 4.31 grams minus 2.00 grams, which gives us 2.31 grams of oxygen. So now that we know that we have 2.31 grams of oxygen and 2.00 grams of lithium, can we calculate the moles from this? Can we calculate moles from mass? Yeah. And then can that give us a mole ratio? Yes. So now let's try to calculate the empirical formula for this compound, and then let's compare it to our predictive formula using charge rules. So you're given the mass of lithium and lithium oxide. And from that, we were able to figure out the mass of oxygen. And your goal is, given these two masses, I want you to calculate the empirical formula. You're going to go through mass and moles to the mole ratio, which is the empirical formula. You don't need it because you have the mass of the two elements. Oh, really? Any questions? Yes.
So what are we supposed to, which is this different?
So in this case, we do a mass percent. And then you look at the mass percentage. This time we're going from just straight mass to and then we will take the mole ratio. So the only thing that's new is instead of working with mass percentage ratio, we're calculating the moles from the mass and then take the mole ratio. Yeah. So this is like the stepwise. Everything going okay? Yep, looks good. Yeah, looks good. Does that match your prediction? Yeah, exactly. Everything going okay? Yeah. So just like in the stepwise method, you calculate you have each of the masses, you calculate each of the masses, then you calculate the moles of each element, and then you take the ratio. Okay. So we have the masses already. And then so this graph is referring to it's easier to write it as monoatomic oxygen. This is just the grams of oxygen. That way you don't have to do a conversion. So you're going to convert each of the masses to moles and then take the molar ratio. Yep, looks good. So I see a lot of reasonable solutions. So let's now continue through with this problem. Everyone's doing quite well on this. I'm hoping that this practice helps because this skill is something that we'll touch on and develop again and again throughout the semester. So I have each of the masses. So my first step is to figure out the moles of lithium. So I'm going to take 2.00 grams of lithium, and to go from mass to moles, what do I divide by? To go from mass to moles, what do I divide by? Molar mass. A key trick that I use is I remember moles need to be on top, and the molar mass of lithium is about what? Yeah, 6.99. Okay, so taking 2 divided by 6.99, that in turn gives us 0.286 moles of lithium. We'll do the exact same process. We'll calculate the moles in the exact same manner for oxygen. So the moles of oxygen, and I really like to write this as, I like to consider, when we say the mass of oxygen, in the context of composition, it's the mass of oxygen atoms. It just saves you so much hassle dealing with molar masses, and it saves you having to do a mole-to-mole conversion. Okay, so we have 2.31 grams of oxygen, and in 1 mole of oxygen, we have how many grams? What is oxygen's molar mass? 16. So 2.31 divided by 16 gives us 0.144 moles of oxygen. Wonderful. Okay, we have the moles, and the empirical formula fundamentally is a ratio of what? Empirical formula is a ratio of moles. Exactly right. Exactly right. So then, the moles of oxygen over the, actually, let's do it the other way. Let's do it the other way. Why would I want to divide the moles of lithium by oxygen? Which number is larger? Moles of lithium. So let's do that. So let's take the moles of lithium over the moles of oxygen. So we have 0.286 moles of lithium over 0.144 moles of oxygen. We end up with 2 moles of lithium over 1 mole of oxygen. So what would our empirical formula be? Li, how many lithiums? 2. How many oxygens? 1. Does this match our predictions if we use our charges, lithium plus, O2 minus, we cross our charges? Does that match our prediction? Yes. So that's a way of checking your work. You don't always have this luxury if your metal is a transition metal. And that's why I'm showing you this example, because there's a bit of guardrails in this example. On the exam, there may not be a way to check using this method. But I would always look for this. If you can figure out the formula using an easier method, use the easier method. There's no reason to do math if you don't have to. Does that make sense? Okay. So if you skipped all of this and you just wrote this out and you wrote this formula, you'd still get to the same answer. But this method is more general than just for fixed charge and main group metals. Okay. Let's tackle one more example. This one is a bit of a puzzle. I always like these kind of problems where you can apply algebra to solve a chemical problem. So I'm going to really let you tussle with this, as this is sort of an exam level question. A compound with the formula KClOx was found to be 28.9% chlorine by mass. I'd like you to tell me what is the value of X, and I'd like you to name this compound. So let me So this is a higher order reasoning question, and my hint to you, write out what does the mass percent represent and write out how the mass percent is calculated. Okay? This one will likely be the last example we'll cover. Not quite. There is an X at the end of it. So there's anywhere from 1 to numbers you can think of. So your job is to figure out how many oxygens do you have. And the trick is writing out an equation for mass percent. Yes, so try to see how do the numbers fit in and how does X fit into it. When in doubt, write out any formulas or information that you have available, and then try to see if there are equations that you can use. It's simple. Yep, that's one way of doing it. And then from that, if you have the mass of chlorine, can you also figure out the mass of, let's see here. So if you're going through the moles of chlorine, can you figure out the moles of potassium?
Yeah, if I put it over, I think.
Mm-hmm. And then can you figure out from there the mass percentage of potassium?
Yes.
And then from there, can you figure out the remaining mass of oxygen? Mm-hmm. So that's one way of doing it.
If we multiply by 100 grams, it should all equal 100 grams, right?
Yes, yes,
Okay.
exactly. Mm-hmm. Any questions? Looks good so far. And don't be shy to talk amongst your group. There are many ways of solving this problem, and don't be shy to share your solution with your partner. Better to talk it through on problems like this. Everything going on. Okay, so we see. You can, but how about if you're starting to mass, you know the mass percentage. Can you write out an equation for mass percentage? So mass percent is like the mass going over the total mass, right? And from the formula, you can calculate the mass of each element. So like you'll end up with 1%, you'll just exit it. So that's one. Everything going okay? So this is just try to think how do we calculate you're very close. So try to write out the Molar Mass calculation and see how So it's good seeing everyone talk through this problem. I saw at least 3 unique solutions, all of which were perfectly valid throughout this class. So I like these kind of open-ended problems where there's more than one way to reach the target. So the simplest one, or at least the one that requires the least amount of unit conversions, involves thinking about what does mass percent represent. So when we think about the mass percentage of chlorine, what am I fundamentally doing? I'm taking the mass of what? Chlorine. So I'm taking the mass of chlorine divided by the total mass. And what does the total mass represent? The total mass is the molar mass of what? Yep. So I'm dividing by the molar weight of this compound, KClOx, right? There is an old philosophical saying that the most straightforward explanation or straightforward solution is often the one that should be chosen. So then let's now write in and let's write out an expression for our molecular weight. So just like we normally calculate molecular weight, let's plug in and let's write out an equation that portrays our molar mass. So let's add up the mass of every single atom in this molecule. So what's the mass of potassium? What was that? 39.9. So we have 39.9 gram per mole. Okay. And what's the mass of chlorine? Yep, 35.45. And what is the mass of oxygen? 16. Now, the thing that's unique is how many oxygen atoms do we have? And I'm not asking for a number here, not yet. I'm asking for, yes, exactly right. The number of oxygen atoms is indicated by X. Yes. Okay. Now, there are 2 ways to go about this. We're now going to plug in this expression for molar mass into this mass percent equation, and we're going to solve it. That's one way of doing it. If you don't want to solve it, you can literally play the guess and check game, going from 1 to however large until you get a match. So let's now show the algebraic method, because I don't like guess and check if I can help it. So we're going to take the mass percentage of chlorine, and we know the mass percentage of chlorine is 28.9%. So we're going to plug in our 28.9%. Do we know the mass of chlorine? Do we know the mass of chlorine? Yes, it's 35.45. We're then going to divide by our total mass. So we're going to take 39.9 plus 35.45. So we have 75.35 grams plus 16 grams And then let's label the variable in a different color. 16 grams times X, okay? And then times 100%. So do we have the tools available to solve for X? Is this a single equation with just one unknown? Is it? Yes. So if this was not related to chemistry, and I just removed all these percentages in grams, I'm confident everyone here will be able to solve it. So don't let the fact that it's in the context of chemistry get in the way of solving algebraic equations. So you can either guess and check or manually solve it. I'm going to manually solve it just for completeness. So first things first, we're going to move this entire term to the left-hand side. We're going to move this entire term to the left-hand side via multiplication. So we're going to end up with 28.9% times 75.35 grams plus 16 grams times X. And that's equal to 35.45 times 100%. Okay, we're now going to keep going with this. We're now going to isolate X. And the way that we're going to isolate X is we're going to divide by this 28.9 term. So we have 75.35 grams plus 16 grams times X is equal to 35.45 over 28.9 times 100%. We're then going to further isolate by subtracting this 75.35. So we have 16 grams times X is equal to, and let's resolve this ratio as a number. So I'm converting this number and we get 122.66 grams minus 75.35 grams. And then finally, we're just going to divide both sides by 16 grams. And that in turn gives us a value of X. And let's punch this into our calculator together. We're taking 122.66 minus 75.35. Everyone following so far in their calculator? And then we're then going to divide by 16. And we get a nice clean number, very close to what? 2.95 is very close to 3. There we go. So X is equal to 3. A lot of work for something very simple. So then our formula would be KClO. Plugging in for X, how many oxygens do we have? 3, exactly. KClO3. Would someone like to finish off this problem by telling me the name of KClO3? Potassium chlorate. Exactly right. Exactly right. So let's write this out. Does this problem make sense to everyone? Does the way that we solve this make sense? Are we using any equation that we haven't seen before? Are we doing anything that we fundamentally haven't seen before? No, fundamentally we're still using the mass percent equation. The only thing that's new and the only thing that you need to know how to do is to take this equation and solve for an unknown if needed. Yes? The X came from the fact that in the formula was given as KClOx. And X is the number of oxygen atoms. So when we calculate our molar mass, we have the mass of oxygen times the number, which is X. And that's what we're solving. So that's all we have time for today. I hope these examples were good practice. And I hope that you attempt the additional examples found in the homework. Make sure you're doing the homework and pre-lecture quizzes. And I'll have another batch of pre-lecture quizzes prepared for Thursday. So you'll have plenty of practice questions. If you need additional practice, the optional homework with the key is a wonderful source. It's a really good idea to look into that. What? Yes, I have the keys for all of them already provided. Okay, and that's it for today.